Um, we're continuing with cell biology and life science in a nutshell. Um, Hope you are able to hear. So, in this section, we're doing a little bit about, um, well, it's organic chemistry. Learning about some of the molecular aspects of uh, important um, components of biology. Um, Cells are obviously made out of um, proteins as well as different kinds of molecules. Lipids, which we learned about. So um, there's certain factors that affect the way that molecules behave inside of cells, and their bonding and the atoms that make up molecules affect the polarities and the non-polarities of molecules, so which affect their function within cells. So um, so Phospholipids, which we learned make up membranes of cells. They're molecules which are very important, and phospholipids are a unique kind of molecule because they have a polar and a non-polar um, aspect. So they have fatty acid tails, which are non-polar, and they have a phosphate group bound to an alcohol, which is polar, on a glycerol backbone. And these molecules interact with proteins, with various molecules that are important for self signaling and interactions within tissues. And there are things called different kinds of bonds which affect how the polarity of the head groups and affect the signaling and the function of molecules. So on the surface of the cell, and how they work as channels, letting in other molecules, etc., working as receptors. So um, in this example, you have an ether bond, which is shown. Ether bonds are carbon, oxygen, carbon bonds, all single bonds. Ester bonds are um, uh, they have same thing that an ether has: carbon, oxygen, carbon, but they also have an extra double bond to an oxygen. So that's an ester bond. So depending on what kind of linkages you have, it depends on determines the polarity of molecules. So these kinds of linkages are also referred to as functional groups. In organic chemistry, functional groups are specific substituents or moieties within molecules responsible for the characteristic chemical reactions of those molecules. The same functional group will undergo the same or similar chemical reactions regardless of the size of the molecule it is part of. Furthermore, the reactivity of a functional group can be modified by other functional groups nearby. In organic synthesis, functional groups that are introverted is a basic type of transformation. Functional groups are groups of one or more atoms of distinctive chemical properties, no matter what they're attached to. The atoms of functional groups are linked to each other and to the rest of the molecule by covalent bonds. For repeating units of polymers, functional groups attach to their nonpolar core of carbon atoms and thus add chemical character to carbon chains, as I just mentioned. Functional groups can be charged. Example in carboxylate salts COO, which are negatively charged due to the oxygen, which turns the molecule into a polyatomic ion or complex ion. Functional groups binding to a central atom in a coordination complex are called ligands. Complexation and solvation are also caused by specific interactions of functional groups. In the common rule of thumb, like dissolves like, it is the shared or mutually well interacting functional groups which give rise to solubility. For example, sugar dissolves in water because both share the hydroxyl functional group OH, and hydroxyl interact strongly with each other. So water as well as sugars have OH groups. Plus, when functional groups are more electronegative than atoms they attach to, the functional groups will become polar. So the functional groups um, when they bind to nonpolar molecules, these molecules also become polar due to the functional groups, therefore becoming soluble in aqueous environments. Combining the names of functional groups with names of parent alkanes generates the systematic nomenclature terms for naming organic compounds. In traditional nomenclature, the first carbon after the carbon that attaches to the functional group is called the alpha carbon, second beta carbon, third gamma carbon, etc. If there's another functional group at a carbon, it may be named with a Greek letter. For example, the gamma amine in gamma aminobutyric acid is on the third carbon of the carbon chain attached to the carboxylic acetic acid group. So there are some charts here, so you can look at these groups. So alkane So the functional groups are groups of atoms in organic molecules responsible for characteristic chemical reactions of those molecules. And the general formula shown here in the diagram of each functional group, R represents the rest of the molecule, which is not as crucial in how the molecule reacts. The functional groups determine specificity of what the molecule will function as. So alkanes, alkynes. You have single, double, and triple bond between two carbons. Alcohol is OH. Ether is an oxygen with two substrate groups. So let's see. Epoxide is similar